Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like efficient MPI programming, MPI performance tools, communication parameters. Let's get started. Slide 1. Efficient MPI Programming Introduction. Today, we are discussing efficient MPI programming, which is a crucial part of high-performance computing when working with distributed memory systems. MPI stands for Message Passing Interface, and it helps in distributing tasks among different processes in a cluster. However, just using MPI is not enough. We need to write efficient MPI code to ensure our programs run fast and use resources optimally. Efficient MPI programming focuses on reducing communication overhead and making the best use of available hardware. Without efficiency, even powerful parallel systems can run slowly because of communication delays and imbalances. In large-scale scientific or engineering simulations, these small inefficiencies can cause huge performance losses. For example, if we are multiplying matrices using MPI and our communication is not optimized, most of the time might be spent waiting for data instead of computing, which we definitely want to avoid. Hence, MPI performance tools and communication parameters are used to identify and fix such issues. Slide 2. MPI Performance Tools Basics. To write efficient MPI code, we first need to analyze the performance of our existing MPI programs. This is where MPI performance tools come into play. These tools help us find performance bottlenecks, places where our program is running slow, maybe because of too much communication, poor load balancing, or inefficient MPI calls. Some tools measure how much time is spent in computation vs communication. For example, MPIP is a lightweight tool that shows which MPI functions are taking the most time. Tau, Tuning and Analysis Utilities, is another tool that provides a detailed analysis, including where processes are waiting. Scalaska focuses on analyzing communication patterns and highlighting inefficiencies, which is especially useful for big programs running on many processes. Vampire and Intel Trace Analyzer and Collector, ITAC, are graphical tools that allow us to visualize what is happening inside our MPI program, like when and where communication happens. Using these tools, we can see if some processes are idling while others are working, which is a clear sign of poor efficiency. For example, if an MPI_B cast call is taking a long time, these tools will highlight it, prompting us to optimize that part of the code. Slide 3. MPI Performance Tools Advantages and Disadvantages. Now, let's look at the advantages and disadvantages of using MPI performance tools. Advantages first. 1. These tools can easily detect communication bottlenecks, which are otherwise very hard to find manually. 2. They analyze the usage patterns of MPI calls, showing us which calls are problematic. 3. Help in balancing load among different processes so that no one process becomes a bottleneck. 4. Measure important aspects like latency and bandwidth, so we know if the network itself is slowing us down. 5. Visualization tools help us understand program flow, making debugging and optimization easier. 6. They are essential for checking if our program will scale well on larger clusters. 7. Provide accurate measurements, helping in fine-tuning of MPI code. 8. Save development time by quickly pointing out issues. 9. Help debug parallel and distributed applications efficiently. Disadvantages. 1. Some tools slow down the program as they analyze it. This is called profiling overhead. 2. Learning these tools takes effort, as they require specific knowledge. 3. Large datasets generated by these tools can be hard to analyze. 4. Not all tools are free or open source. 5. Output from these tools may need expert interpretation. 6. Some tools might not support all MPI versions, limiting usability. 7. Limited support for hybrid programs, MPI plus Open. 8. Too much detailed data may confuse beginners. 9. Developers may become too dependent on tools and ignore basic optimization principles. So, while these tools are powerful, they need to be used wisely and with some learning. Slide 4. Communication parameters in MPI definition and significance. Next, we'll discuss MPI communication parameters. These are settings and tunable options that influence how MPI handles communication between processes. Sometimes, by simply tuning these parameters, we can significantly improve the performance of our MPI programs. For instance, if we adjust the buffer size properly, we can avoid communication delays. Some key parameters include: 1. Message size, the amount of data sent in one communication. Sending too much or too little can both be inefficient. 2. Latency, the time delay before a message starts transferring. Lower latency means faster startup of communication. 3. Bandwidth, how much data can be transferred per second. Higher bandwidth means faster communication. 4. Buffer size, the memory space reserved for sending, receiving data. Small buffer might cause waits, large buffer might waste memory. 5. Number of processes, how many parallel units are communicating. More processes can mean more overhead if not handled well. 6. Synchronization method, like blocking, wait until done, or non-blocking, continue without waiting. 7. Topology settings, logical arrangement of processes, e.g., grids, rings. It affects how data flows between processes. Example: if we set a message size that matches the network's optimal transfer size, we avoid breaking messages into smaller chunks, thus speeding up communication. So, tuning communication parameters is essential for achieving efficient and scalable MPI programs. Slide 5. Advantages and disadvantages of tuning communication parameters. Let's now discuss advantages and disadvantages of tuning communication parameters. Advantages. 1. Reduces communication latency, making data transfer faster. 2. Utilizes bandwidth efficiently, leading to quicker communication. 3. Helps balance load effectively across processes. 4. Reduces idle time, where some processes wait for others. 5. Improves scalability of the application when running on large systems. 6. Minimizes delays in collective operations like MPI_barrier or MPI_gather. 7. Makes the best use of hardware resources like network and memory. 8. Helps in overlapping computation and communication, improving overall speed. 9. Gives programmers control over communication behavior. Disadvantages. 1. Incorrect tuning can actually hurt performance. 2. Finding optimal values can be complex and time-consuming. 3. Needs deep knowledge of both hardware and software behavior. 4. Sometimes requires trial and error, which is effort-consuming. 5. Settings may not be portable across different machines. 6. Setting large buffers may cause memory issues. 7. Misconfiguration may cause deadlocks or synchronization issues. 8. Sometimes, performance gain is minor for the effort invested. 9. Requires frequent tuning if problem size or hardware changes. Thus, while tuning is powerful, it needs to be approached with care and understanding. Slide 6. Ways to achieve efficient MPI programming. Finally, let's discuss practical ways to write efficient MPI programs. 1. Use collective communication like MPI_bcast, MPI_scatter, MPI_gather instead of many point-to-point messages. This reduces the total number of communications. 2. Avoid unnecessary synchronization, like repeated MPI_barrier, which can cause delays. 3. Use non-blocking communication, MPI underscore I send MPI underscore I receive to overlap data transfer with computation. This way, processors don't sit idle waiting for data. 4. Optimize message sizes, combine small messages to reduce overhead. 5. Reduce communication frequency, send only essential data, not everything. 6. Balance computation and communication, divide work so all processes are busy. 7. Use virtual topologies to organize processes logically, especially for structured problems like matrix operations. 8. Profile and analyze code regularly using MPI tools to identify and fix issues. 9. Example: in a matrix multiplication, instead of sending one row at a time, batch multiple rows together to reduce communication overhead. By following these practices, we can ensure our MPI applications run faster and utilize resources effectively.